So after the one, so we can start Jay Prakash. You can start Jay Prakash.
Okay, ma'am. Thank you.
Good afternoon.
Good afternoon, sir. Welcome, sir.
Good afternoon. Can you hear me?
Yes, sir. Yes, sir.
Okay. Okay.
Jay Prakash, you can start now.
Okay. Coming together is a beginning. Keeping together is a progress. Working together is success. Good afternoon to everyone. I feel honored to welcome one and all for the international webinar Analysis in Data Science, organized by the Department of Electronics and Communication Engineering in association with International Research and Collaboration Cell. I am sure that you all will feel enriched with the knowledge after and to invite Mrs. U. Jayalakshmi, HOD of ECE, to deliver the welcome address. Please, ma'am.
Yes, thank you, Jay Prakash. Good afternoon to one and all present here. On behalf of Electronics and Communication Engineering Department, International Relations and Collaboration Cell, and on my own behalf, I extend a cordial welcome to everyone for the international webinar on applications of topological data analysis. I would like to express my sincere gratitude to our founder chancellor, Dr. A.C. Shanmugam, and our Honorable President, Engineer A.C.S. Arun Kumar, for their unwavering support and encouragement in organizing today's event. It is indeed my great pleasure to welcome our respected Vice Chancellor, Dr. S. Geeta Lakshmi, who has been a pillar of strength in all our achievements. Madam will be joining us shortly. I feel delighted in welcoming our rector, Dr. D. Vishwanathan, who promotes enthusiasm among us in all our endeavors. Welcome, sir. I am glad to welcome our director, IQAC, Dr. K. Balasubramanian, who serves as a motivational resource for all our undertakings. Welcome, sir. With great honor and privilege, I welcome among us the guest speaker of the day, Dr. R.U. Gopidasan, Associate Professor from Faculty of Ocean Engineering Technology and Informatics, University of Malaysia, Terengganu. Sir, we realize that it takes a great deal to remove some time from your busy schedule and come over here to share your expertise. Thank you for accepting our invitation. Welcome, sir. I'm very happy in welcoming all my fellow colleagues and dear students and the participants from Malaysia to utilize the platform to the best of their abilities. I, along with Dean Dr. R. Kausalya and the organizing secretary, Dr. K. Daman, would like to once again welcome you all to the event, and I'm confident that you will all take some productive learning home with you today. Have a good time ahead. Thank you.
Thank you, ma'am, for the warm words of welcome. It gives us immense pleasure to invite Dr. D. Vishwanathan, Rector, to deliver the facilitation address. Please, sir.
Good afternoon, ladies and gentlemen. Respected speaker from Malaysia, Dr. Gopidasan, distinguished faculties, respected HOD, respected Vice Chancellor, ladies and gentlemen. I'm extremely happy to join with you all in this international webinar. And the topic is topological data analysis in data science. At the outset, I would like to congratulate the faculties of ECE who is organizing this program, and they have taken up a very recent development in this field, which is emerging from various works of applied algebraic topology. So I, on behalf of MGR University, I welcome and thank Dr. Gopidasan for readily accepted and giving international lecture. MGR University is a pioneering university in whichever the latest development comes up, we take up and to the students. Little I know about topological data analysis because I am not a computer person or electronic person. I am a mechanical, generally mechanical field. But little the recent developments I came to know on topological data analysis. This topological data analysis is a recent field that emerged from various works in applied topology and computational geometry. It is used to analyze the data set from topology techniques. In applied mathematics, topological based data analysis is an approach to the analysis of data sets using techniques from topology. Extraction of information from data sets that are high dimensional, incomplete, and noisy is generally challenging. TDA provides a general framework to analyze such data in a manner that is insensitive to the particular metric chosen and provides dimensionality, reduction, and robustness to noise. Beyond this, it inherits functionality, a fundamental concept of modern mathematics, from its topological nature, which allows it to adapt to new mathematical tools. This initial motivation is to study the shape of data. TDA has combined algebraic topology and other tools from pure mathematics to allow mathematically rigorous study of shape. The main tool is persistent homology, an adaptation of homology to point cloud data. Persistent homology has been applied to many types of data across many fields. Moreover, its mathematical foundation is also theoretical importance. The unique features of TDA make it a promising bridge between topology and geometry. The characteristics of TDA in application are combining tools from several branches of mathematics, quantitative analysis, and the role of short persistence. The applications of TDA are signal analysis, propagation of contagions on network, graph reconstruction, fractal geometry, complex network, image analysis, sensor network, etc. So like this, we are very eager to learn from Dr. Kobidasan, and this field will enhance our students' future career. I thank all the participants and the organizers for giving me this opportunity. I wish the program all success. Thank you.
Thank you, sir, for giving us a basic idea about the concept and for the good wishes for a long run. Now I request Dr. K. Balasubramaniam, Dean, IQAC, to convey the special address.
Good afternoon to all. First of all, I congratulate our EASY department faculty members and students, as well as the International Relations and Collaboration Center for organizing an international webinar on the topic of application of topological data analysis in data science by our professor, Dr. Gobidasan, University of Malaysia. First of all, I welcome our friend, Professor Dr. Gobidasan, for this webinar, and thanks for accepting to deliver, to talk on this international webinar. Nowadays, data science is one of the emerging and growing technology in computer science and engineering. The data science is the evaluation of mathematical statistics and data analysis and big data. It is an interdisciplinary field, and to allow to extract data from structured as well as the unstructured data to eliminate the frauds in machine learning algorithms. At the same time, data science can help us to detect the frauds and also to recommend the right product to the right customer. In data science, various languages like Python, C, C++, and SQL, and HTML, and so on, are used in data science. So I ask all our student friends to learn at least 2 languages from the above set language for getting a better placement in this time. With this, once again, I thank our today's speaker, Professor Dr. Gopinathan, University of Malaysia. Welcome for today's international webinar. And at the same time, once again, I my best wishes to our ECE department of faculty members and coordinators for this webinar. Thank you.
Thank you, sir, for your valuable suggestions to the gatherings. Moving ahead into the session, now I invite Dr. M. Kumaresan, Professor, ECE Department, to introduce the guest speaker, Dr. R.U. Govidasan. Sir, please.
Thank you. Good afternoon, everyone. I would like to introduce Dr. Gopidasan Rudruswamy. He is Computational Department of Mathematics, Faculty of Arts and Engineering Technologies and Informatics, University of Malaysia, Terengganu. His qualifications, he has completed his PhD in Mathematics, University Science of Malaysia, Master of Science, Mathematics in USM, a Bachelor of Applied Sciences in Computer Modeling, USM. His research area is like numerical methods, computer-aided geometric designs, topological data analysis, social network analysis, and data visualizations. His professional qualifications, he is certified as a Google Professional Online and Cloud Trainer, a Microsoft Certified Professional Developers, and Microsoft Certified Technological Specialist. He has attended and also conducted many number of online events, online certified programs. He has published around 50 articles in reputed journals like national and international journals. He also published books, and also he has published many number of articles in proceedings. He received the grant for formulation of a free curves on the surface and also a theoretical analysis of trimmed surface connections and reconstructions of trimmed surface of high quality from 3D point clouds. It's the grant in aid of scientific research from Japanese government. So he has a lot of grants from that various agencies. He has been he worked as the project head and co-researchers in national and university level. This research area his research area, Internet of Things, embedded system, Raspberry Pi. Okay. Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you.
Thank you, sir. Education is not the learning of facts, but the training of mind to think. With an inspirational quote by Albert Einstein, I consider it a great honor to welcome Dr. R.U. Govidasan to take over the session. Please.
Hello, very good evening. Can everybody hear me?
So good evening, sir. Yes, sir.
Okay, so it's clear, right?
Yes, sir.
Okay, so I am Govidasan, and a very good evening to everyone. All right, so this is my first time with MGR University. Okay, so I've been like writing names so that I can address you correctly. First of all, Ms. Ilakia and Mr. Jay Prakash, actually playing the chairman role, I suppose. So first of all, thank you to both of you. And then just now, a number of VIPs, I think, talked, right? So first of all, thank you to Dr. Kumaresan introducing me and reading out my biography. And also thank you to Dr. Vishwanathan for introducing on TDA, Topological Data Analysis, which I would be talking about in a while, right? So these are the names that I actually picked up. And also special thanks to Dr. Kausalya. She's the point of contact for me to MGR University. So she's the one who actually approached me last week and then made this program today, right? Make its program available today, right? And so I would like, again, I would like to say a very good evening to everyone, respected HOD, Vice Chancellors, faculty members of MGR University, and also students, right? So there are also a number of faculty members from my university, right? So welcome everyone. So let me just start, right? Okay, so I will now share my slide. So I can't share my slide now. So I think you have to enable for me to share my slide.
Just a second, sir. Check. So kindly check now, sir.
Right, I can share my slide now. Right. Okay. Give me a minute. Right. So can everyone see my slide?
Yes, sir. Yes.
Okay. So, okay, let me start. So I am Gopi Dasan, and I'm currently attached with University Malaysia Terengganu. Okay, so I'm now with the Faculty of Ocean Engineering, Technology and Informatics, and we also have a special interest group, which I'm attached with. It's called Special Interest Group on Modeling and Data Analytics. Okay, so today's talk would be very much introductory of topological data analysis. So we are going to go through what it is. And then after that, I will show you applications in the context of data science. Okay, so now this would be the content, table of content for today, right? First of all, a little bit on data science, very little, because I need time to talk about topological data analysis. So as Dr. Vishwanathan put it, one of the methodology for topological data analysis would be on persistent homology, right? So we're going to look at a little bit on topology, and then after that, we're going to move on persistent homology, and then how we can use persistent homology to identify the topological signature of data and use it for machine learning. Okay, so that's how it's going to be. Right. So we know data science, right? So even I forgot just now, Dr. Balasubramaniam, in fact, talked about data science, right? So data science is, as he put it, data science evolved from originally it was just statistics, right? People take data and then they crunch data using statistics, right? The statistics was very much under the umbrella of mathematics, right? But now data science is kind of like a mixture right? A mixture of three important entities. The first of course, computer science, and then we have mathematics and statistics, and also the domain knowledge itself, right? For example, if you do data science for biology, then you need to know the content of biology itself, right? So it's a nice mixture of all these three entities, right? And also, Dr. Vishwanathan talked about extracting information, right? So we have data, we want to extract information, and this information sometimes very much in a very high dimension, right? At times it's also incomplete and also noisy. So this makes life very, very hard, right? So we tend to like spend a lot of time to clean the data, and then after that do some sort of like crunching and processing of the data, such a way that we get a useful insight or in order to make a proper decision, right? So that's very short in terms of what is data science, right? And then let's look at the cycle of data science, right? A very simplified form, yeah? So first of all, let me, okay. So we have some sort of like a business understanding. So we have some question that we want to know, some information that we want to extract. So we first of all, of course, we accumulate data, enough data, and then we do all those cleaning, right? So after cleaning the data, so we will then go to machine learning, right? So in machine learning, there are two important entities. First is model training. So we have estimators, right? You're going to use some sort of a method as with data to estimate and predict, right? So first is the estimator, and then once we tune the estimator, we have a model, working model, and then we'll go to prediction, and then we will check how good is our model, right? Okay, so this part here basically on machine learning, which I would go through in a while, right? So one important information that we need in order to do a proper model would be on extracting the feature. So we have a proper label of feature from the data, then we would be able to train our model to be accurate, right? So it's kind of like very important here. So there are many kinds of feature extraction methods available there, right? For example, a simple way would be, let's take PCA, principal component, right? So we can just extract the principal component of high dimension data, make it into a small, lower dimension, and then use it to do estimation, and then train, and then do validation, and then we can do prediction, right? But there are things that we will lose, right? When we do PCA, there are some of information that we might lose, right? So we will look at it in a while. Okay, now next is very much once you have your model, then you will do based on your prediction, you will make your decision, and then we follow. Next would be on monitoring, right? So basically, you will monitor the performance of your model, and then you will recollect the data again, and this is the cycle, right? So we will evolve over time. We will retune our model over time, such a way that the prediction is gives us a better decision making solution. Right. So we now roughly know what is the cycle of data science. Now let's go into the details of topological data analysis. Right. A simple example here. So this is called a data source dozen, right? So as you can see here, this is the first set of data, which looks like a dinosaur, the head of the dinosaur, right? And what they did is that a group of researchers, what they did is that they took this data, they used a method called simulated annealing, and they tried to match the different kind of geometries. For example, here you can see a star, right? So from this data set, which looks like the head of a dinosaur, they try to fit to a star, right? With conditions that the mean, the x mean and y mean, basically this is in 2 dimensions, so we have x values and y values, is the same, right? So, and then the standard deviation of X, the standard deviation of Y is also the same, and the correlation also the same, right? So basically all this data, all this point cloud, we have about 12 point cloud, that is why it's called data source, right? So all this data has same mean in terms of X and Y, same standard deviation correlation. So since that is the case, how would you even be able to differentiate between this data, right? So here, what we can see is that the failure of statistics, right? So basically we use the mean and standard deviation correlation in order to describe the data, but unfortunately, we can't use it here to differentiate between this data, right? What is so obvious is that by just looking at it, we would be able to classify what is what, right? So the whatever that we did through statistics, it's very much on quantitative, right? Very much quantitative approach. Whereas if by looking at the shape, right? By looking at the shape, we would be able to differentiate, right? So by looking at the shape, this is called qualitative approach, right? So qualitative approach basically means that we will investigate the shape of the data, right? And then when the dimension of the data is very high, right? For example, this is just 2 dimensions, so we can still plot and look at it and then try to classify it. But if it is in a higher dimension, we would not be able to look at it. So we need a tool, right? We need a tool to quantify the shape of the data such a way that we can classify them. So let's look at, for example, this is another example, right? So we have 4 point clouds, A, B, C, and D, right? So it has different kind of behavior, right? The first data is very much the correlation between X and Y, very much linear, we can see. So we can use a regression method, for example, to fit a line and then do prediction. Whereas B is very much clustered, right? The data is in the form of clusters, what, 3 clusters. A C, it's a mixture of cluster and flare, right? We have 3 flares, right? 1, 2, 3, in which all this data meet in the middle, right? Finally, we have one data which has a shape of a circle, right? So all this data we can visually see, and in its lower dimension, we would be able to somewhat quantify the shape. We want to quantify the shape and represent that quantification as an indicator or a label to do machine learning, right? So that is the idea actually. Okay, so a little bit on topology, right? So the take of topological data analysis is data has shape, right? So when we have the shape, right? Once we can quantify the shape, right, then we can do a lot of things, right? So basically, we would use topological data analysis to quantify the shape. Now, the advantage of TDA is we can investigate the data at a different scale, at a different resolution, right? When I show you the method, you would see why and how TDA would be able to look at the different resolution and different scale, right? And it is also resistant to noise and missing data. Let's say a number of data is missing in your point cloud, it would still be able to capture the shape of the data, right? And it is also invariance under deformation. Basically, topology itself, it's due to the idea of stretching and resizing, but at the same time keeping the shape intact, right? So topological data analysis can be a very good tool to explore your data, right? So it can fall under the category of exploratory data analysis as well. Yeah. So the output of TDA would be your topological thumbprint, right? In which we look at in a global and local way, right? Okay. It's okay if you can't follow currently, but I'll be showing you some examples for you to understand better. Now, there are 2 methodologies for topological data analysis. So as you can see here, the first one would be on persistent homology, And the next one would be on TDA mapper, right? Now imagine you have this data set, right? This data set, the data set is something like number 8, right? Number 8 in this form, or you can say it as like looks like an infinity sign, right? So which has a small hole and a big hole in this data, right? So if it goes in a persistent homology, you would get a diagram. So this is the diagram, this is the output that you would get. Yeah, so if it goes to the second methodology, which is mapper, sorry, you would actually get a graph, right? So this graph is basically the topological structure of this data, right? So assuming that this small hole is insignificant, so you would get this kind of graph which indicates that there is a big hole in your data, right? Whereas when it goes on the left hand side, which is persistent homology, so you would get a graph in this form. What does this graph say is that, for example, you can see this is a diagonal line, right? This is a diagonal line, as you can see. There are, when you get points far away from the diagonal line, yeah, for example, you have 2 points here, right? So these 2 points basically indicating those holes, right? Okay, so basically what it means is that persistent homology is the study of holes, actually, the study of n-dimensional hole. Yeah, so let's go into detail of persistent homology. I think okay, right. We can skip this now. Let's look at a little bit more on topology, right? So basically, topology is the study of shape, right? In a higher dimension, right? So if you look at a book, an important book on algebraic topology by Mankras, the first sentence would be this, actually. A fundamental problem of topology is that determining whether given two spaces are homeomorphic, right? So we need to, like, we want to differentiate between two objects, whether they are similar or not, right? That is actually the study of topology, right? So homeomorphic, there's one important word here, homeomorphic. Homeomorphism means shapes that can be deformed into each other without cutting or gluing, right? So it's though like you are playing with a Play-Doh, right? Where you can pull and push, as long as you don't cut it or you don't poke a hole, right? For example, if you have a ball here, right? So you can squeeze and make it in an ellipse, or you can just squeeze and make it in a very much this form, right? So the sign here means the ball is homeomorphic to this shape. Yeah, this ball sphere is homeomorphic to this shape, right? Whereas you have also seen a coffee cup, right? This coffee cup has one hole here, so you can see, right? So you can squeeze and make it such a way that it becomes a torus, right? A donut shape, right? In which there's one hole still remaining as it is, right? You can also make it very much in a crooked donut this way, right? Again, the one hole remains as it is, right? But if you look at sphere here on the left-hand side, and then if you compare to the donut on the right-hand side, it is not homeomorphic because we have lost the information of one hole there, right? So this so-called I was talking in the form of a whole, right? So it's actually called invariant in mathematics, right? Invariant in mathematics. So basically, as I said earlier, topological data analysis is actually keeping track of all the holes in the data. Okay. Now, in mathematics, right, especially in topology, we actually quantify the holes using a Betti number. All right. So the definition is that kth Betti number refers to the number of k-dimensional holes in topological space. Okay, so we have the subscript Betti beta 0, right? The subscript 0 here means it's the number of connected components. We have Betti 1, yeah, means a number of one-dimensional hole, also kiloholes. Betti 2 means number of two-dimensional voids. Then we can also just extend to kth dimensional hole, right? So which we denote as beta k. Okay. Now what we're going to do now is that once we have our data, we are going to quantify those, quantify the topological information in the data by counting the holes actually, right? That is the idea. Now, let's look at some examples to understand Betti number better. Okay, so this is just 2 points connected with a line, right? So Betti 0 means, as I said, connected component. Basically, there is only one component here. So Betti 0 is actually 1. And Betti 1, if you still remember, represents one-dimensional hole. Since there is no hole here, so it's actually 0. Okay. Now let's look at a circle. Okay. Now the circle is just one component. So we have Betti 0 as 1. Okay. And Betti 1, a circle has one hole, one-dimensional hole. As you can see, it is actually, so it is 1. So beta 0 is 1, beta 1 is 1. Okay, so the Betti number for connected component is 1, just one component here. And then Betti 1, which represents one-dimensional hole, as 1 as well. So whereas if you look at here, we have 3 disks, right? So it's shaded means it's a disk. So we have 3 disks. So we have 3 connected components. So Betti 0 is actually 3. Whereas Betti 1 is actually 0 because we don't have holes in this set. And this here is actually analysis, just like your CD, right? Analysis, we have a hole in the middle. So of course, Betti 1 will be 1 and just one component. So we have one component here. Betti 0 represents 1. And here it's an example of a graph, right? A graph which with vertices and edges connected together. So we can also count a number of connected components and also holes in this graph. Yeah. For example, there are 2 components, as you can see, one component here and another component here. So we have 2 components representing Betti 0 as 2, whereas Betti 1 would be how many? Right? We just count here 1, 2, and 3. Okay, so we have actually 3 holes here, right? So there's another way to actually identify the number of holes where you need to cut through and count number of cuts that you make such a way that it doesn't break, right? For example, if we have a circle here, right? If I cut here, it becomes one straight one, like let's say this is made out of thread. If I cut here, I get one straight thread here, right? And it's still staying intact. So that is why I can make one cut, but still keeping one component. So Betti 1 is 1, right? Whereas here, I can make one cut here. This one stays as one component. I can cut here twice. It will stay as one component as well. So that is why 3. If I make more cuts, we're going to get more components, which we don't want, right? So that is how we can actually count Betti 1 physically, right? Okay, so roughly you know now how to count the number of holes, right? So you know how to count the number of holes. So let's look at this example. So this is an example of simplicial complex. It's just like a triangulation in 2 dimensions, right? So the triangles, as you can see, the triangles, sometimes it's not really triangle. Yeah, we have connected components in such a way, right? But it has also faces, which I have shaded in blue, right? So this is actually simplicial complex, right? Simplicial
sir.
complex. In 2-dimensional, it's just like a graph. 1-dimensional is just like a graph, right?
Sir,
Okay.
sir, sorry to interrupt, sir. Our Vice Chancellor, Madam, has joined us.
Okay.
Ma'am, welcome, ma'am.
Just now I landed up in Chennai. So since this is a very good program of in your field, I wanted to wish Gopi Dasan to welcome to our Dr. NGR Educational Research Institute to deliver his knowledgeable thoughts and the processes to be done by our faculty and our students. And I should appreciate Jayalakshmi and her team who have worked upon this program for quite a bit time and got you to deliver your thoughtful and knowledgeable talk. Thank you, Jayalakshmi. Thank you, Gopi Dasan, for joining us.
Thank you, Dr. Gita Lakshmi, as a Vice Chancellor, for your welcome. Thank you very much. So should we continue?
Yes, sir, sure, sir.
Okay. So as I was saying, right, so basically topological data analysis, so far what I've said is that we are just trying to count the holes, right? Count the holes in our data, right? So very much we are very much, just like by looking at it, we're trying to count the holes, right? For example, now let's look at this simplicial complex. Okay. So remember, Betty 0 is just number of components. So we have one huge component here, so which is 1. So another one here, and another one here, and then another one here. Finally, just one node by itself. So we have 1, 2, 3, 4, 5. So Betty 0 is actually 5, representing 5 components, right? Now Betty 1, what would be Betty 1? Betty 1, if you still remember, is just number of holes in the simplicial complex, right? One-dimensional hole. So we have one-dimensional hole here, 1. Another dimensional one-dimensional hole here, so becomes 2. And we have 1 here, 3. Another one here, 4. So Betty 1 would be 4, right? Would there be any void or 2-dimensional hole? We would not have 2-dimensional hole in this R2, right? This is just in R2, so there won't be any 2-dimensional hole. Okay, it's just 0, right? So if you go even higher, there won't be any any holes in higher dimension. This is just well defined in R2. Okay, so basically by looking at it, you'd be able to count what is Betty 0, Betty 1, and Betty 2, right? So far, so good. Okay. Now we can also count the holes for any kind of manifold, right? Any kind of manifold. For example, here I have a Mobius strip, right? So for Mobius strip, as you can see, it's just one component, right? So Betty 0 will be 1, and this Mobius strip has one hole here in the middle. So Betty 1 is actually 1. While here, it's interesting because we have one component, so Betty 0 is 1. Betty 1 would be 0. There's no one-dimensional hole, but we have two-dimensional hole here. Imagine this is your football, right? So there's two-dimensional hole, but there is no one-dimensional hole, right? So this is a good example of having two-dimensional hole. For torus, right? For torus in mathematics, the torus is actually empty in the middle. So that is why our two-dimensional hole is actually, we have just one, right? Which one? The one that we're representing in the middle. Whereas Betty 1 is actually 2. Now, remember, as I said, we can actually physically check, right? Physically check by just cutting through, right? So how many cuts you can make such a way that it stays as one component? How many cuts? But the thing is that you have to cut through, right? So for example, one cut you can make here, and another cut you can make go around it, So you have made 2 cuts. Beyond that, you can't make any more cuts. Otherwise, it will become 2 components, right? So that is why BT1 is 2. So basically, we have 2 kind of holes here, 1-dimensional holes here actually. Okay. So now the data is different, right? The data is very much in the form of point cloud, right? We have point clouds. So from the point cloud, we have to create a simplicial complex, right? From the point cloud, we have to create a simplicial complex. From the simplicial complex, we would actually count the holes, right? Okay. Now, let me show you a simple example how to do that, right? Give me a minute. I think a simple example would be nice to show you how we make simplicial complex out of point cloud, right? So give me a minute. Okay, so all right, let me can you see? Can you see? Can you see the holes? I mean, sorry, can you see the point cloud? Can you see the simulation?
Yes, sir. We can see.
Great. All right. So example, this is an example. Yeah? This is an example of we have a number of points, right? So what we do is that we first of all, we draw a ball for each point cloud. This ball has an increasing radius. So the radius usually we denote as epsilon, right? So as we increase the ball going to overlap, right? When the ball overlaps, we draw an edge, you see? When the ball overlaps, we draw an edge. When 3 balls overlap, we get a face in which we get a nice triangle, a closed triangle, right? But for example, here, the triangle is not closed yet. We get to get a triangle. Once all 3 overlaps, then we get a triangle. So as we increase the ball, we get an open ball, open triangle, which is a hole. The triangle with the hole, for example, there's one hole here, right? So you can see, okay, now we have 1 hole. We have 2 holes, so 1 big hole and a small hole, right? So that is how now we keep track of the birth of a hole, and also we keep track of the depth of the hole. For example, the small hole is still there as I increase. Now the small holes has died, right? So for example, again, now the small hole is there. As I increase, now the small hole is died. When died means that it's closed by the face of a triangle, right? And as I can increase further and further and further, now the big hole has died as well. So again, let me just go through. Okay, this is the presence, the birth of a big hole. It leaves, and it leaves. It's about to die and it dies off, right? So what we do is that we keep the information of the birth of a hole and the death of the hole, and we are going to keep track of all this, whether big or small holes, right? We are going to keep all those information. So basically, we're going to keep the information of the birth and death of the holes, right? As we increase the radius, right? Now, when I show this, you should be able to think with in the form of your data, right? So your data right? When I said we are looking at a different resolution, means is that this is what it means. I'm not looking at one resolution, but I'm looking at a different resolution, right? From local to global, right? By keeping track of this information of the holes, we would be able to do a lot of things. Okay, so that is what I'm going to explain in a while now. Okay. Now let me bring back the slide. Okay. Give me a minute. Okay. Okay. So now you know how we create simplicial complex, right? How we create simplicial complex. Simplicial complex are created based on some rules, how the balls overlap, right? So there are many kinds of simplicial complex that you can make, right? One example is called a check complex. It's just that the way it overlaps, right? The way it overlaps, just now you saw, the way it overlaps, then we create edges and faces. We have a lot of other complexes as well, right? I would actually go a little bit into it at the end of the talk. Okay. Now we know how to do simplicial complex with the balls, and then we can keep track of the birth and death of all those holes, right? Now, this is the so-called the flow of keeping track of the holes, right? Which is persistent homology. We are going to compute the number of holes in your data, right? First, what we do is that we start with creating simplicial complex. Why I do that? Because I want to represent your data in the form of a geometry, such a way that I would be able to quantify the shapes. Again, we can roughly say quantifying the number of holes there, right? At a different scale, right? Okay, now, after doing this, right? After doing this, we are going to quantify, as I said, quantify the number of holes. So basically, in algebraic topology, what we do is that we keep track of the boundary matrix, right? The boundary matrix basically would keep track of the birth and death of all the holes, actually. From the boundary matrix, it's just a matrix, we would be able to reduce it, right? It's just like a row reduced form, which you used to do in university. We can do some algebra to the matrix such a way that we can compute the holes, right? Not just the connected components, but various kind of holes. If you still remember, right, I represent it in the form of Betty numbers, right? So in algebraic topology, the holes are basically the quotient group of the kernel quotient by kernel quotient by its image, right? So you get the H0 as its homology group. The rank of H, so-called H hand here, is your Bn's Betty number. Okay, so anyway, this is very much in the form of homology, right? In the form of algebraic topology. But here we would be able to do it by just doing matrix reduction. Okay, so which means we can compute beautifully, right? Now, so once we compute we compute the matrix, we do matrix reduction, we would get actually a persistence diagram. Remember, just now I showed you a persistent diagram would be the representation of your data, right? The topological representation of your data. So from persistent diagram, we can actually represent it in many ways. We can even do some sort of statistical methods in persistent diagram in order to understand better about the data, right? Okay. In fact, what we would I will later show is that taking persistent diagram as its topological signature, we will be able to do machine learning. Okay. Now, so these are 4 steps for topological data analysis. All right. So just now you saw that how we increase the radius of the ball such a way that keep track of the birth and death of the holes. Okay. Now, so I have 3 examples here. So 3 different a point cloud. Yeah, so a point cloud, I represent it in the form of x1, x2, and x3. So on top. So once I do persistence, once I do filtration simply means keeping track of the birth and death of the holes. I would be able to represent it in the form of barcode. Okay, this is a barcode. Okay, so an example here is that we have the red color would represent the connected components, right? If you still remember, as I increase the simplicial complex, I increase the radius of the balls for each point, the points are getting connected, right? The points are getting connected. So we actually count how the points are getting connected until the last one would be infinity, where all the points are now clumped together, right? So when the points connects to another point, then we get, instead of 2 components, we get 1 component. So that is how the points are getting connected and becoming 1, right? So that is actually the red one represents connected component, right? The birth and death of that component, right? So basically here we have another kind of barcode, which is in green color. So this barcode represents the holes of 1 dimension. Yeah. So of course we keep track of, as I said, the birth and death, right? For example, here we have a birth of 1 hole, and then it took some time. It persists over the radius, and it died after around here, right? So probably this hole here, it persists over some radius. So the longer the barcode, the more persist the hole is, right? The more prominent the hole is. For example, here there are 2 holes persist over some radius, right? And here we can see there's 1 hole, there's another hole actually where the birth and death is somewhat short as compared to this hole here, right? So now roughly you get to see how we keep track and then represent it in the form of a diagram. But this diagram here is called a barcode. Okay, this barcode basically encodes the topological signature of your data. Now, another representation would be, yeah, this is another example of a barcode for this point cloud here, right? So another representation of a barcode would be persistence diagram. Okay, so instead of drawing in the form of a line graph, B1 the birth and then D1 is the death of a 1 point, 1 hole, we represent it as a point in in 1 dimensional space, right? Where X represents the birth and Y represents the death of the pair. Okay, so for example, here is actually representing this long bar here. Okay, so the birth time is B1 and the death time is D1, right? So it's far away from this diagonal line. And this diagonal line represents the same time of birth and death, right? B equals to D. So when the points are on this, you know it's not prominent. The hole is not prominent at all. In fact, we can actually just label all those points as just noises, right? The one is far away from this diagonal line. For example, this point is the prominent hole in that in our point cloud. So there's another one as well, right here. So as you can see, the simplicial complex here, right? So there are two holes which persist over some radius, right? So that is these 2 points here. Whereas the rest of the holes are somewhat noisy kind of holes, right? So it's not so prominent, right? Now, from point cloud, we get a barcode. In fact, we can also represent in another form, which is a persistence diagram. So the blue one would be H1, representing 1-dimensional hole, and the red one would be connected components, how they are getting clumped together, right? Connected components. So this is actually the topological signature of your data. Okay, so your diagram, which I label as DGM, right? Your diagram is actually just a collection of points of birth and death. Okay, so that is your diagram. Now, what we can do with the diagram? So before we go to that, let's look at examples of persistent diagram for a number of manifold that we know. For example, here we have a point cloud representing a circle. If you still remember, just now I showed the circle. A circle has actually one dimensional hole, and it's just one connected component, right? So you would get this persistence diagram actually, where the orange color H1 represents the one-dimensional hole that you get from your point cloud here, the circle. Yeah, this one here. And now this is sphere, collection of points presenting a sphere. A sphere has, let's look at here, a sphere has two-dimensional hole. Yeah, a void, just like a ball. There's nothing hollow. There's hollow in the middle. So a white two-dimensional. There's no one-dimensional hole, H1. So we don't get. All these are noisy, very much near to the diagonal line, which indicates all these are noisy points, right? So actually, there's no one prominent one-dimensional hole, right? There's two-dimensional hole, no one-dimensional hole, but of course we have one connected component. Okay, so that is how we read persistence diagram. Another one here, torus, right? So for torus, we can see there's one-dimensional hole, 2 points here, and one two-dimensional hole, right? So we can exactly encode the topological structure by using persistent homology. Okay, so you can reflect to what I showed earlier here, yeah, from the persistence diagram. Okay. Now we have persistence diagram. So what I can do with persistent diagram? So far, what I know is that persistent diagram represents the topological signature of my data, right? So what I did is that I took my persistence diagram, I created my simplicial complex. After creating those simplicial complex by varying the radius of the ball, I obtain my topological signature in the form of persistence diagram. Now, using this persistence diagram, for example, taking the maximum persistence, right? Maximum persistence simply means is that death minus birth, right? Death minus birth will be the lifetime of this point here. So that we can also find this one, death minus birth, and we can take the maximum value of death minus birth representing the biggest hole in this your data, right? So which is far away. Right, so we can just take that information alone to do a lot of things actually, right? So now here, by taking this, I can also vectorize them, right? So usually machine learning needs a vector, right? Needs a vector to do either if you want to represent, you want to do some sort of machine learning. So we need actually vector, right? So what we need to do is that we need to vectorize this persistence diagram, right? One way to do it would be by representing in the form of persistence landscape. Okay, so how we do it, right? Okay, there are two steps actually. Taking this persistence diagram and vectorizing it into persistence landscape. There are two steps to it. The first step would be, for example, this is your persistence diagram. Yeah, you have your points, and what you do is first is that you transform to a new so-called a new axis, which represents this axis here, right? First, the first step. The next step would be to represent a tent function, a linear function. Yeah, piecewise linear function. And you draw those linear functions. After drawing those linear functions, you identify the maximum persistence. For example, the maximum value of those 10 functions. For example, here, this would be the maximum value, right? So inside this maximum value, we can draw another layer of maximum value as well. So this is a second maximum value of the 10th function. So we can actually get layers of maximum value for the next maximum value and next maximum value, right? So these are in fact, the vector, a long vector representing the so-called n-dimensional whole from your persistence diagram, right? So basically, why we did that is that instead of just collection of points, I want to do some sort of like vectorization such a way that I can give it to machine learning to do training and testing, right? There are some information that we would not be able to extract from here. A simple thing like what if I want to take the average of 2 points? I just can't do by just adding 2 points and get the average. The average here would not be unique, which is a failure of computing a space. That is why we need to represent it in the form of persistent landscape. It's another way of representing your topological signature of your data. Okay, now, so this is one way, persistent landscape. Another way would be to represent it in the form of persistence diagram. How we do it? Okay, it's somewhat similar, but this time around, we are going to give a distribution for each point, right? So you have your persistence diagram, right? So first what you do is that you rotate 45 degrees. So you get this form. And after that, you give a distribution. For example, a Gaussian distribution for each point, right? You give Gaussian distribution to each point, right? Or you can also give weight. For example, the height of this, you give the weight. After that, you can give Gaussian distribution as well, right? So there are a number of parameters that you can play around, such a way that get an image out of it. Image basically means a table, right? Image basically means a table, and this table has a pixel, right? The image has a pixel, so each pixel actually an element for a matrix. So we can take this again, which is in the form of vector now, and do machine learning. Okay, so basically I have explained 2 ways: taking persistence diagram and representing it either in the form of persistence landscape or persistence diagram for machine learning. Now, there's also another way, right? For example, if you want to do machine learning, the first thing you need, for example, if you want to do support vector machine, right? SVM, you want to do that, you need the distance matrix. How far is one point to another, right? Similarly, here we can get the distance between 2 persistence diagram. It is an example of a kernel function, right? So a kernel function is that takes a pair of a diagram and as input and outputs a real value, right? For example, a simple, I would say a simple kernel function between 2 points would be the distance, right? We compute the distance how far from each other, right? So we can also do that, right? We take 2 persistence diagram. For example, here I have 2 point cloud here. The first point cloud will be in blue color. The next one is somewhat a noisy point cloud representing a circle as well in orange color, right? So we have 2 persistent diagram. So how we compute the distance between these 2 persistent diagram is that, for example, in here we have 2 ways. One is called bottleneck. The other one is called Wasserstein distance, right? So bottleneck, basically what we do is that you try to match who's close to who. For example, the blue one represents for the blue point cloud. The orange would be the persistent diagram for the orange point cloud. So when you match them to each other, this is a match, and then you find the distance, the maximum distance, just minus the differences between the X and Y element, and you add it up, you get bottleneck distance. Whereas Wasserstein distance would be, you have to compute for every single point, and then you add them up, right? For example, if there is no match, you're going to match it to the diagonal line and find the distance, right? So that is how you find a bottleneck and Wasserstein distance. So basically, again, why I do that? I want to compare between two persistence diagram and find the distance. Again, why I do that? Because I want to know how different one point cloud to another in the form of its topological signature. Okay, so taking this information, you can just put it in machine learning and do your classification or clustering. Okay. Okay, so another two examples, right? For example, I have 2-point cloud, right? So this for the first one is kind of a circle, right? And I have its persistence diagram here, just one prominent one-dimensional hole. Another one, I have a point cloud which represents a bull's eye. Yeah, so I have one prominent hole, but then the rest is not so prominent. Okay, and here, this one here, basically the bottleneck. So I get the bottleneck distance, which I compare this two persistent diagram. The bottleneck distance will be 21.9. Whereas the Wasserstein distance, as I said, I try to match first. After that, I find the distance. The rest I find the distance as well. If no match, I just match it to the diagonal line and find the distance, and then compute sum up in order to get its Wasserstein distance, which is here is about 41.7. So different kind of distances, depends which one you want to use for your machine learning method. Okay. Now let's move on examples for machine learning, right? So there are a lot of tools, TDA tools out there, open source TDA tools, right? Since originally when they built it, it was all alone by itself, right? So we had different kind of TDA tools out there, but eventually we know that it's not going to work by itself. It's better to work along with other machine learning methods, right? So since they know scikit-learn is one of the famous machine learning methods and tools, so what they did is that they just like created an extra feature such a way that they can use the outcome of a topological data analysis and just put it in machine learning and do the processing. Okay, so examples of those kind of tools are, the first one would be scikit-TDA, right? So the second one would be this is the somewhat like a very new version of TDA, which is called GeoTool-TDA. And this is kind of very old and a lot of user. It's called Goody, right? So basically all these three are running based on Python, right? And it's on Python, and then the core would be running on C++. Okay, so I'll show examples. Okay, so again, so first of all, just now I showed you a simple cycle of machine learning, right? So we have data aggregation, we have data wrangling, data cleaning, and then we need to transform the data. We get do some sort of feature engineering. Only then we do machine learning. And this is the standard way of doing it. But this time around, we are going to use topological data analysis. So what we do is that we need to do some sort of we need to change the data so that we can do TDA, right? We will get its persistence diagram. And then from persistent diagram, we would vectorize the diagram and then use this as a label and then put it in machine learning and train our model. Okay, so that's what we're going to do now. So the first example, remember I showed this this set of data just to show example how I can use this data to create clusters, right? So I want to actually cluster them and see how the clusters, what is clustering to what, right? So that would be my first example. The next example would be on periodicity, right? So we are going to take a gene expression and then we are going to rank it based on topological data analysis signature, which is persistent homology. And finally, classification for dynamical system. Okay, right. How long do I have? Yeah, how long do I have? Can someone tell me? Mr. J. Prakash? Hello?
Yes, sir.
How long do I have?
10 minutes, sir. Shall we
Okay.
wind up by 3:30, sir?
10
Yes,
minutes.
sir. Thank you.
Is it? 10 minutes, right?
Yes, sir. Yes.
Okay. All right. So, okay, let me show a few examples. So let me just sum up. And then now, this is the first example, right? So what I did is that I took all this data set and I first get the topological signature in the form of persistence diagram. After getting the persistence diagram, I get the distance, right? So for example, here I would actually extract the distance of bottleneck for each persistent diagram. So pairwise distance for each. After getting that distance, for example, I took, as I said, I took a bottleneck distance, and then I put it into a simple hierarchical clustering problem, right? Clustering tool. So when I put it, instead of a standard distance, I put bottleneck distance. So this is what I get, right? So you can see that how different can an X shape and a circle be. So this is the so-called the accumulation of clusters from the shape of X to circle, right? And we can also see a cluster of bullseye, away, and star, right? So this is bullseye, and this is away and star, right? So we can now clearly see why they are clumped together, right? Whereas the rest of it are somewhat far away from this cluster. And of course, circle is somewhat very special. It is by a cluster by itself, right? So bottleneck distance, which is the so-called the differences between persistence diagram, could actually encode how far from how different one point cloud to another. Okay, that is one example. The next example is you want to cluster your time series. Since I suppose you guys are in engineering field of study, you might do time series clustering or ranking, right? So how this is an example, 3 examples of time series. Yeah, we have Y1, Y2, and Y3, and you can see the rate one is actually having a damping effect, right? So the rate one having a damping effect. So if you do a standard way, right? If you compare a standard way using dynamic time wrapping, right? So you would get this cluster, right? So dynamic time wrapping is the standard method used for clustering time series. So you get, this is the outcome of your cluster where Y1 and Y2 are clustered together, which is really wrong, right? So if you do persistent homology, in which what I did here is that from time series, I embed in higher dimension using Tuck-Kane's embedding. This is something like a transformer where from one dimension, we increase its dimension. After increasing the dimension, we then extract its persistence diagram. Using just the maximum persistence, I then construct the dissimilarity matrix. Using this dissimilarity matrix and input for my hierarchical clustering, and then I do the clustering. So once you do that, you will be able to see that the damping is very much far away to Y1 and Y2, which has nice periodicity. Okay, that's another example. So I'm going to skip examples, don't have much time. Okay, this would be also a very interesting example, suppose. Okay, so this is an example of supervised classification. So supervised classification of orbits from a twisted map, right? So we have a twisted map, right? It's actually basically, we're trying to extract the information of a dynamical system, right? This is actually a dynamic system represents two elements, X and Y. We have X and Y element. So we kickstart with a random number. We have one parameter here, R, right? So I can give different values of R in order to get different dynamics and orbits. Okay. So let's look at what will happen if I give some R, right? Okay. For example, if I set R equals to 2.5, so this is the dynamics I get. As you can see, the point clouds are somewhat scattered, right? So of course, I would be able to encode it in the form of topological signature. So this is the persistence diagram of R here, of R 2.5. I can in fact convert it into a persistence landscape. So this is how the persistent landscape looks like, right? So this resolution of persistent landscape here I set from 0 to 100. So each piecewise function would have actually 100 points. Okay, so it's a vectorized representation of persistence diagram. So this is another example when R equals to 3.5. So again, it's persistent diagram, this corresponding persistence landscape. So somewhat different, you can see somewhat different. Now, when R equals to 4.0, so you get somewhat like an empty space in the middle, a hole here. Of course, persistence diagram can really encode that. So we get a nice one-dimensional hole here. And this is its corresponding persistent landscape. And then when R is 4.1, the hole is kind of like enlarging. So of course, you will get a further away point. And this is persistent landscape. And finally, last example, R is 4.3. When R is 4.3, you see different dynamics where you get different two voids actually. Two holes here, somewhat two holes here. So again, we get a nice 2 points here. There's also another one here. I'm not sure which one is that, but that is the topological signature of this point cloud, and this is its persistence representation, persistent landscape. Yeah, not diagram, persistence landscape. So this is the persistent landscape so far we have obtained, right? So we can use this information rather than using the points itself. We will use this information, and then these are the labels, right? These are known labels that we know. So I name as the first one as class 0 and R is 2.5 until I have class 1, class 2, class 3, and this is class 4. Typo there, class 4, representing 4.3. So I have the labels, I have the representation of the data, which is in the form of topological signature. Again, to be specific, it's a persistence landscape, right? Now, what I did here is that to experiment it out to see how good we can use, how good it would be to use the persistence landscape rather than the point itself, right? So what I did here is that I have 5 classes, right? For each class, I created 10 simulations. So for class 0, which is R equals to 2.5, I created 10. And then for R 3.5, created 10. Until R 4.3, I created 10. So I have 5 classes, I created 10. Each 10 simulation, each I get 50 point clouds. So 50 point clouds. So each 50 point clouds, I extracted the persistence diagram. So now I have 15 point clouds, I have its labels. So what I did is that I shuffle it and I split it into tests. So I have 10 test data, test set of its point cloud and also its label, and I have 40 to train. Okay, so my pipeline to train would be, first of all, I'm not using H0, I'm not using connected component, I'm just going to use H1, yeah, one-dimensional hole, right? The holes that you saw earlier. So H1. So I will first, what I do is I normalize the diagram. Normalize means you just, it has got different values. So I normalize it from 0 to 1. Once I normalize it, and then I extract its persistent landscape with resolution to 100. Yeah, each layer. That persistent landscape means it has got many layers. I'm going to take first 5 layers, and then each layer is going to be represented with 100 points. So this is a long vector. Using this vector, I'm going to use random forest to do a model, right? So in here, of course, I'm going to do a little bit of a hyperparameter tuning. So I'm going to do cross validation. I'm going to break the train into another 5 set. So one set I'm going to use it as to test, another 4 I'm going to use to train, and then I'm going to just tune it such a way that finally I get the best model, right? So by setting pipeline and then doing hyperparameter tuning with the grid search CV is actually very much straightforward in Python. Now, then I validate, right? So once I get the model, I validate with the test, the 10 tests which I split just now. So the train accuracy is about 1. The test accuracy can be from 0.9 to 0.8, right? It's very good, right? Even though I have just 40 set of data, I still can get from 0.9 to 0.8 accuracy, right? So of course, now what we can do is that using this model, if you have a new set of data, new set of point cloud, and then you will be able to somehow identify what R would it be, right? So this is a simple example, right? A simple example available out there in which how you can use persistence diagram here, specifically persistent landscape, to train your model rather than the data itself, right? To train and then to predict for example, here to predict R, right? So this is how you can do it, okay? Now, the sources available out there, as I said, there are many sources. Just now, I showed you what I showed you is the outcome of GUTI, right? Of course, as I said, they are very much close to scikit-learn. So the outcome of this, you can put it into whatever scikit-learn's tools that you have in order to do your machine learning task, right? Now, there are different kind of complexes that you can use, right? So I always get this question, which complex to use, right? For example, if you use GUTI, you want to use if you have your data in a lower dimension, you want to use alpha complex. Alpha complex will be the best complex because it also involves Delaunay triangulation, right? So it's the best to use if your data in a lower dimension, right? If you a bit higher dimension, your data is in a higher dimension, you should use a check complex, right? Check complex is a more dedicated complex in which it can encode the n-dimensional whole. Whereas if your data is really in a high dimension, you should then go to Vittori-Strips complex. Why? Because it is the so-called the approximation of check complex, right? So in fact, the relation between all these three is that alpha complex is actually a subset of check complex. Again, check complex is a subset of Vittori-Strips complex. Okay. There are also, if you use an image, right? You take an image, you want to encode its topology. You can also do that. Sorry, topological signature. You can also do that. You should do it with cubical complex. Okay, so you have cubical complex as well. And in any case, if your data is a bit noisy and etc., so there's a new complex that has been created by a group of researchers from Fujitsu, Japan. It's called DTM, distance to measure complex. So you can, all these are available in GUTI, right? So there is some note on using complex that you want. There are also tools out there. If you're using MATLAB, there are also tools out there. It's called a JavaPlex. So it's a tool freely available that you can, if you search in the internet, you will get to do TDA computation. Okay, so acknowledgement. So this my work TDA is actually funded by Ministry of Education Malaysia with a grant called Fundamental Research Grant Scheme. And then I also like to thank a number of researchers, my colleagues. Paul Lotglo is now currently attached with the Polish Academy of Science, and a friend of mine, Vidit Nanda, helped me on studying the TDA. Also Martin Crossley, who helped me with topology, right? And also a special thank goes to Dr. Kausalya, which she's actually the point of contact to MGR University. And here, I think Dr. Kausalya is very much a friend of Associate Professor Dr. Unjiu. So both of them actually made this talk possible. So with that, thank you very much. If you like the codes that I showed you just now, I can just upload it in GitHub and then share it to you. So probably I will share it to you here. And after that, I will let Dr. Kausalya know when I upload it in the GitHub, and then you'll be able to use it. So with that, thank you very much for your time and attention. Over to you, Mr. Jay Prakash, and I think Miss Elakia.
Thank you, sir. Thank you so much, sir. It was exceedingly informative session, and the knowledge shared will definitely help us a long way throughout our journey and for achieving success in various disciplines, sir. Thank you so much, sir. Now we move ahead into Q&A session and interaction session. The participants as well as the students are requested to post their queries in the chat box.
Okay.
Sir, Lakshmi, sir.
Chat box. Okay.
Hello, am I audible?
Yes,
Yes,
yes.
Sir.
Yeah, good evening. Good evening to all the participants. Right. So I have a question from Rahul. Sir, sir, for a multivariate type data set, which is the best algorithm to understand the relation between variables? This is the question being asked by Rahul, one of the students.
Okay. I am not a statistic expert, but anyway, multivariable simply means is that you have data sets, right? You have for example, it's actually multivariable data set can be related to higher dimension data set, which means imagine now you have multivariable simply means you have many columns representing many features, right? Many columns representing many features, and then you have many observations. So this is very much a high dimension data set. In order to understand the relationship, you want to find correlation, that's one way to go, right? You can just visualize and see how related they are. You can do different kind of tests, right? Whether the variants are the same. If you want to do tests whether the variants are the same, you can do homogeneity test, right? So, but it's not. I'm not a statistic expert, so I would not be able to answer you that. But if you just to answer your question, you can do correlation, right? And also you can do a homogeneity test to see how the variants, whether the variants are the same or not, right? If the variants are the same, you know the data looks almost similar. Okay, and of course you can do topology. You can also obtain the topological signature of the data, but it has got nothing to do with this question actually. Does that answer your question? Okay.
Thank you, sir.
Welcome.
And I have a question, sir. How far the topological data analysis is effective in nonlinear networks?
Can you define what is a nonlinear network?
Nonlinear means I can say that the relationship, you cannot predict the output of a system or a network. You can randomly.
Okay. No, I do understand on nonlinear. Can you explain about network? It's a graph?
Yeah, something like. If it is a nonlinear system, how far your TDA is effective in nonlinear networks?
Okay, I don't understand what you mean by network here. Network here means a graph.
What I'm talking about nonlinear means.
Nonlinear, it's okay. Nonlinear, understand, but network.
Cause and effect, right?
You're saying something?
See, so input-output relationship is not well defined.
Input, output.
Cause and effect, I can say like that.
Cost and effect. So, for example, just now you saw a dynamical system, right?
Yeah.
Yeah, I go down. Here, okay, this is an example of a dynamical system, right? It is very much, sometimes it's just chaos. For example, here, for r equals to 2.5, you can see it's very much random. The points are very much random. So you can't really.
Non-linear system, right?
Sorry? You said something?
Yeah, chaos. Chaos is a typical example of a non-linear system.
Right. So what we did here is that we tried to extract its topological signature, and then we did machine learning in order to understand how can we predict R, right?
Yeah.
That is what we did here. And your question is, how can we?
Yeah, how it can be effective in addressing the non-linear problems in the networks, wherever you have such non-linear problems.
Address here. What do you mean address? You want to understand, is it?
Yeah. Yeah.
So here, what we did is that we created a model actually, right? So you can see we actually created a model using random forest machine learning method. So once we have a model, so basically if we have a new set of data, right, we can just put it in and predict what kind of R would it be, right? So it will give, the output would be a class in which you would be able to figure out what is R, right? So in this context, right, so of course, the topological signature basically represents the so-called non-linearity of the system, right? Which is very effective, right?
Yeah.
Instead of just using the points and just putting that, right? So basically all the points, right? Because of course you can just take all the points and then try to do machine learning, but it's not really effective because the non-linearity actually has its shape in n-dimensional space. So does that answer your question?
Okay, okay. Thank you, sir. And I have another question, sir. Actually, nowadays, a lot of people are getting addicted to social networks, something like WhatsApp, Insta, Twitter, something like that. And so whether this TDA can be useful in analyzing the what I can say is accessibility of people in a social network.
Okay, so the presence.
Yeah, whether it will be able to analyze, say, these type of people are getting addicted to this type of ideology or this type of interest they are having, something like that. So how it is getting exploited by the PDA technology.
Okay, so basically, there's another methodology that I did not describe. It's called mapper, right? It's called mapper. So here, when you put a collection of points, so these points are basically representing whatever points that whatever data that you collected from social media, the presence and etc. So basically, what you do is that you take this data and put it in this mapper. The outcome would be a graph, something like that, right? So a graph here, like for example here, right? So you can see the relation between a collection of how they are clumped together, right? And then when you can just call it back and see what it means. So here, what it does is that it shows the whole structure of whatever data that you use. So for example, use your social media presence in WhatsApp and etc. You put it there, and you'll see how they are related to each other. Right. So this method is actually used for fraud analysis, and a lot of work actually. A lot of, for example, yeah, here, financial crimes, disease recovery, genomics. So if you want to ask and answer the question that you asked just now, you should go for PDA mapper.
Okay. Okay.
Right.
Thank you, sir.
All right.
Sir, I have a question. This is Dr. Suraman here. Am I audible?
Yes.
Yes, sir. For topological data analysis to be used, say, for example, if it is a supervised learning system, or if I have a data set, or I can map it to a supervised learning, that means already learned model or some model is available based on your data set, say a vehicle classification problem. So I will fix it to a particular already worked out data set and I will do the analysis. What for if I have an unsupervised learning? How will I go about with the analysis?
Okay, right. So unsupervised learning, basically clustering, right? Basically clustering. For example, you saw, oh, give me a minute. Oops, sorry. Okay, so for example here, right? So what I did is that a collection of points, then I'm trying to cluster them, and first I'm trying to just cluster them. Just take the topological signature of each data, I just clustered them. So from here I know, right, I've clustered them, like for example, roughly about 3 clusters, right? So from these 3 clusters, then I do somewhat like semi-supervised, right? So basically what I did is that from this cluster, I understood that I had some 3 clusters. From there, I do classification, right? So if you first you understand the cluster, all right? After understanding the clusters, how many classes are there, and then you do classification. For example, they said just now vehicle classification, right? Okay, so you move from unsupervised, then you move to supervised. So TDA is basically in between semi-supervised clustering. Does that answer your question?
Yes, sir. Okay, sir.
All right. Again, vehicle clustering would be very nice actually. Yeah, you will have probably you collect a lot of data, right? A lot of features. From there, you'll be able to do to capture its topological signature.
Okay, sir. Thank you.
Sir, Sudaman, sir.
Yes, ma'am.
Sir, please deliver the topic.
Okay, we have come to the end of the session. I take this opportunity to thank our management who has been of our pillar of support on all our even.
So our voice is breaking, I think, seems.
Now, sir? Am I audible?
Sir, it's
Yes,
breaking,
yes.
sir.
So, my due thanks to our management who has been our pillar of support for all our events and arrangements in conducting this type of international events and knowledge sharing sessions. Thanks goes to our president, sir, our vice chancellor, madam, who has delivered her inaugural address, and our rector, sir, Dr. T. Vishwanathan, who has given an introductory speech about applications of data science. And thanks to Director IQACs, Dr. Balasubrahmanian, sir, who has been guiding us to conduct all these international programs and what we take about inference from these programs. Special thanks to the Dean, Dr. Kausalya ma'am, who has been a point of contact with Dr. Gopidasan, sir, for delivering this lecture on applications of topological data analysis in data science. Special thanks to our guest speaker and Sir Dr. Gopidasan, sir, who has given a thoughtful, wonderful session on the analysis of TDA, that is your topological data analysis, how it is useful in supervised as well as unsupervised learning. He has dealt in detail with examples and analysis. So, thanks to our HOD ma'am Professor Jayalakshmi, who is guiding us with all these in the conduction of all these events. Thanks to our event management, event team, who was arranged for our live streaming of this session. Thanks to Ilakya, Ilakya, who has been the host and taking care of all the event management, and special thank all my wonderful colleagues out there who has supported in all the events, and also thanks to Jay Prakash, who is doing the MCing, and all thanks to all the participants, my dear students, and also those who are connected from University of Malaysia, Terengganu. Hope we will continue all these international events to enrich our students with knowledge sharing sessions. Thank you, sir. Thank you, Gopidasan, sir. Thank you so much. Thank you, dear students. Kindly fill up your feedback forms. It is the link is available in the chat box. Thank you. Thank you, sir. Thank you, Gopidasan, sir. Thank you so much.
Thank you.
Sorry, thanks to Kumarasan, sir, who has introduced our guest speaker. Thank you, Kumarasan, sir.
Thanks to all for on behalf of the department.
Thank you, sir. Thank you so much, sir. My participants, kindly fill the feedback form which is shared in the chat box.
So, Miss Ilakya, would that be it?
Yes, sir.
So, is
Shall
that
I-
all?
Yes, sir. No, I'm waiting for the feedback form, sir.
I see. Okay.
Oh, thank you, sir.
So we will wait, is it? We will wait
No,
for a
no,
while,
sir.
yeah?
You can leave, sir.
I see. Okay. So if that is the case, thank you very much
Thank you,
for
sir.
the closing
Thank you so
speech as well, Dr. Sudaman, right? Dr.
Yes,
Sudaman,
sir.
thank you for your closing speech. And thanks everyone for your presentation, for your attention, and also for your time. So I'll now leave, yeah? I'll now leave. Thank you very
Yes,
much.
sir. Sure, sir. Sure, sir.
If you have any questions.
We'll be getting this session material from you.
So you want a PowerPoint?
Yeah.
Okay. All right. So right. So what I will do is that I will pass the PowerPoint, and also I will also upload the codes, whatever the examples that I showed in GitHub, and then share it to Dr. Kausalya.
Okay. Sure. Okay,
so
thank you.
Yeah. So you are always welcome with questions. You can email me your questions.
Sure.
Right? So I will just put my email here as well. Share in chat box if you want. Okay. So that is my email. I think there's one question from Dr. Shaukat. Right. Currently, Dr. Shaukat, I don't have examples for satellite images. Dr. Shaukat, probably we will be sitting down together, and we will start crunching satellite images and see where we can go from there. Right. Of course, we can do quantification of satellite images. Okay. So that's all. Thank you very much, and you have a good day. Right. So if you have any questions, just email me. Right. So thank you very much.
Sure, sir. Sure, sir.
Okay. Bye-bye.
Oh, bye-bye. Have a great day.
Thank you. Ilakya ma'am?
Sir, சொல்லுங்க sir.
எல்லா ஸ்டூடெண்ட்ஸ் எல்லாமே இந்த ஃபீட்பேக் ஃபார்ம் ஃபில் பண்ணிட்டாங்களான்னு செக் பண்ணிக்கோங்க மேம்.
ஓகே சார், நான் ரெஸ்பான்ஸ் செக் பண்ணிக்கிறேன் சார்.
நீங்க க்ளோஸ் பண்ணிக்கோங்க. தேங்க்யூ.
ஓகே சார், தேங்க்யூ.